Okay, so we're gonna go ahead and start with lab number 3. So I noticed that some of you have not completed lab number 3. So I'm gonna go ahead and record it here. That way, whenever you get to it, you have access to this. Now, for this semester is lab number 3. So let's see. For lab number 3, this periodic table in quantum numbers is actually posted on Brightspace. Please notice that I'm going to be using different resources to write because of what I'm working with. For this first paragraph, you want to look at chapter 3. Chapter 3 will actually have the answer in the textbook to this paragraph right here. So it's not actually in chapter 2. So for right now, I'm going to skip over that part. But for this other part here, you're working on complete and fill out the table below. So what you're doing here is you want to work on this after finishing chapter 2 homework, after reviewing chapter 2, because the answers to the questions here are in chapter 2. And if you haven't gone over it, you will not know how to answer these questions. I just realized right now I cannot show this right here. So I have to just enlarge this part. Okay. So you want to know what the four quantum numbers are. Let me go ahead and scroll down because it's towards I can't tell from here because this part is a little bit obscured. But you're looking for the four quantum numbers that help us locate the first three that help us locate the orbital where there's a high probability of finding the electron, right? Remember, you're told here that the plot of distance versus phi squared is drawn, and that's how we get the different shapes of orbital. And what exactly is the orbital? It's a probability distribution map, a region around the nucleus where there's a high probability or chance of finding the electron, where the electron is likely to be found. So for us, we're looking for the orbital because we're looking for the electron. When we find the orbital, we find the electron. The first three quantum numbers over here actually code to the position of the orbital. Then the last quantum number tells us what the electron spin is, okay? So let me go over here. Here it is, okay? So we have this information right here. Let me scoot this over a little bit. It might make what I'm doing a little bit easier. Okay, can I write here? No, this is a different. Let me see if I can draw here. Okay. This is different. Okay, so here I think I answered the first one, right? Principal quantum number, that's the first one that goes with this. And then it says symbol, that will be this. You copy that. Restrictions, so we're told over here, if not here, we're told somewhere beyond here, the possible values of n, okay? So I think I scroll back up again on the left. What am I doing? Oh, let's see. Yeah, right here. We're told that n can be any whole number integer greater than or equal to 1. So that's what I have here. I didn't write all those words, but that's the restrictions. Now, once again, you're writing this for the assignment, but it's also helping you prepare for the exam. And if exam 1 has already passed, then you're preparing for the final, right? So here you want to write as many details as possible. It does describe the energy level of the electron. As n increases, the energy of the electron also increases, and the electron is further away from the nucleus. You want to write enough information so you when you're reviewing this information or this lab, it does actually add to your knowledge, right? Remember the principal quantum number, that name is right here. So we've done this. So you want to do, that would be number 1. You want to, of course, do angular momentum number 2. So just right here, angular momentum. Of course, this would be L, right? And these, by the way, are your PowerPoint slides right here. I'm just literally just copying. And then number 3 here will be magnetic quantum number. So I just call it mag quantum number. The symbol for that will be M sub L, right? Because it's a symbol right here. Oh, it allows me to just, okay. And the last one will be spin quantum number. So that will be number 4 here. That will be spin. And of course, when you want to know the details, spin quantum number is M sub S. You want to scroll down here and click on the PowerPoint, go through, find the details. For right now, we don't need this. So here, L, angular momentum, the second one, or the symbol L, the orbital quantum number, it tells you information here, right? The restrictions are from 0 to n minus -1. So you put it here, it goes from 0 to n power of solar power minus -1. So it goes like that from this to that. Sorry, my handwriting is awful. then you want to write what information this provides. This provides the shape of the orbital. I like to call it the general shape because when you go to the M sub L level, the next level below, that's what gives you the more specific shape and the orientation, right? So you have the general shapes here, the S orbital shape that's spherical. You have the P orbital shape that's like a dumbbell shape. You have the D orbital shape that's a cloverleaf shape. You have the F orbital shape that looks like 8 balloons tied together. And I like to call this the flower shape. It's not really a flower, but yeah. And then they're not asking you for all that though, but just telling you, okay, what information is provided by this angular momentum. Next one we're looking at is magnetic quantum number. For magnetic, I kind of have to skim through it. Oh, there it is. The restriction here is from negative L to positive L. So you write that here, negative L, all the way to positive L. Those are my L's, horrible looking L's. But what information is provided for this? Here you're told it specifies the orientation of the orbit. So we're getting specific shapes and orientation of the orbital on the axes, right? Remember, the orbitals are usually drawn on the axis. You have the X, you have the Y. So you have the X, and then you have the Y, and then you have the Z axes, right? So when you specify the orientation, that is M sub L. And of course, when you get the specific shape. And so we'll go into all of these details later on, but that's pretty much it for the first page. Okay, second page, I actually opted to complete the second one, right? On the second page, you're told for the various combination quantum numbers, L, since now you know what it is, right? So L, M sub S, enter the appropriate information in the following table. Okay, so realize that N is missing here. The energy level is missing. When it comes to the L values, let me go back here because I know this is very abstract. Let me go back to the slide that has this information right here. I think I had it. Yes. So remember the quantum numbers can be represented sometimes as letters or numbers, right? In the case of L, that's very, very, very strong. L can be represented as numbers or as letters, right? So for the different values of L, we actually have the letter S that corresponds with when L is equal to 0, right? We have the letter P that corresponds with when L is equal to 1. We have the letter D that corresponds with when L is equal to 2. And the letter F that corresponds with when L is equal to 3. Okay, so the first thing they're asking me here for is the numbers, and I've gone ahead and answered the second one. So, of course, for the numbers, not the letters, you put L is 0, L is 1, L is 2, L is 3, right? I'm not going to work on the whole thing. Okay, now I want to tell you something. There is some kind of sequence here and some kind of correlation. When they're asking you for type of orbitals here, they're asking you for the letters that correlate with this. So of course, you know when L is 0, the type of orbital will be an S orbital. When L is 1, the type of orbital will be a P orbital, right? Okay, now we'll get to the rest of this. Okay, the next thing is M sub L. So I'm going to scroll down here to your slide and find M sub L. Once again, I'm not necessarily reteaching this. I'm just trying to show you where the answers are. Okay, we know from lecture that M sub L, can I get a blank slide here? Oh, great. Okay, hold on a second. Let me try to see if I can. Oh, I need to get out of this mode. Okay. Okay, yeah, I'm going to delete this. So I can actually. Okay, give me just a sec. Okay, so I'm on this blank here so I can go ahead and write a little bit more. Okay, so when we're writing the M sub L value, remember the M sub L value relates to the L value, right? So I want these side by side so y'all can see. Okay. Somewhere in the lesson, when I go over the pop and explain to you how this works together, right? So I'm just relating the L. Oh, where it is? How do I make this work? The L value to the M sub L value. Okay. I think I need a little bit more space for this. So let me see. Move this over. So we have the L value here. I'm trying to correlate this to the M sub L value. Okay. Now we're told the way these are related to each other is this way. In the first page, you said the M sub L, to get the M sub L, the restrictions are start with the L value, right? The negative L value, increase this by 1 because they're integers, all the way to 0, right? And keep increasing this by 1 all the way to positive L. So not only is this the restriction, it's also the formula. So I get to review this here. Since for the most part in the periodic table we have 4 different values of L. Then you start with when L is 0. Oh, I wrote too big. When L is 1, when L is 2, and when L is 3. Okay? So when L is 0, M sub L, I guess you can write it as negative 0, comma 0, positive 0. But what exactly is negative 0 and positive 0? They're still 0, right? So we don't write all that. So what we say here, oops, I erased too much. What we say here is when L is 0, M sub L is 0, okay? When L is 1, M sub L has to start with negative L. So it starts with negative 1, comma, 0, because you go all the way to 0, and then you stop at positive L, so positive 1, okay? And that's what I've worked on here. This goes with this one here and that part. So what you're going to write then is for number 2, you're starting with negative L. So that would be negative 2, comma, negative 1. And you see in the sequence here, right? You're adding 1 each time to go to the next level of M sub L. And this is going to be 0, plus 1. And then you stop at plus L, plus 2. Okay? I'm going to let you guys finish the sequence here. Okay. Because you guys have to do something on your own, right? Okay. So then, of course, that will go over here. And the tricky part on this one here, though, is M sub S. We don't have enough room for M sub S. It's tricky. So here's the thing. What I've tried to do in the past is write this vertically because we don't have a lot of room. Let me try to do that over here. We know when L is 0, M sub L is 0, right? So remember, M sub L codes for the orbital. Now I'm going to go back to the analogy I told you guys about in lecture. The orbital is like, it's a 3D region. It's like a shape, a space, a sphere, different shapes, right? So I like to look at it as a room. It's a room where we find it's a room called the orbital where we find the electron. And sometimes the room is empty. So we see the orbital is empty. Sometimes the room has 1 electron, or sometimes the room has 2 electrons. If it has 2 electrons, the electrons have to have opposite spins, right? And that was a rule by Pauli that we talk about in the next chapter. Anyway, back to this topic here. So for the M sub S, you're assuming that the orbitals, which is what M sub L is, these are orbitals. Each of these numbers here are orbitals. Let's see, I can write. Okay, each of these are orbitals. We're assuming that they're fully occupied by electrons, right? And remember, we learned this rule that 1 orbital can house 2 electrons, right? So I like to write these vertically. And the way we write the electrons according to M sub S, with M sub S, get 2 possible values of M sub S. The first M sub S is usually plus 1/2. That corresponds with the first electron in the orbital. The second one is minus 1/2. I kind of decided last minute to record this, so hopefully everything is going well. Okay, so every number in M sub L codes to a shape. Every number in M sub L is equal to 1 quote unquote orbital or house where the maximum electrons you can have in there are 2. So when I look at this right here, I want to show you this. The negative 1 orbital has these 2 electrons. Let me try to use different colors to make a point, okay? And then the next one will be a 0 orbital, this pink one here, houses these 2 electrons right here, okay? And then the last one will be, let's make it green. Okay, so this would be a green orbital right here, plus 1, that will house these 2 electrons. So you see the challenge here, right? The one that has 5 M sub L values will have 10 electrons. So let's go ahead and show this right here. Since over here you have negative 2, I'm going to write this with negative 2, negative 1, 0, plus 1, and plus 2, This is plus 1 and plus 2. I'm struggling to write. Over here in the M sub S, for every M sub L, you will write positive 1/2 and then negative 1/2, the second electron. For the next one, positive 1/2 and then negative 1/2. The next one, positive 1/2. I'm running out of room, right? Negative 1/2. Okay, next one, positive 1/2, negative 1/2. So you have to do this 5 times because you have 5 different M sub L's. Positive 1/2, negative 1/2. So of course, for number 3, where you have 7 different M sub L's, you have to do this 7 times. You're going to have 7 pairs. Okay, I'm not going to work on that. I already struggled with this one here, so I'm going to move on. Remember, with the type of orbital here, the order is SPDF. So I'm going to let you guys finish that part. Okay, this L relates to this number right here, and then the letter, right? Type of orbital. M sub L actually relates to the number of orbitals of this type. Okay, we saw right here that we only have one. This is just one type, right? We have one type of S orbital. And we saw before it's a sphere, right? We have 3 types of P orbitals. So that's what we have here. So this is usually one type. We have 3 types here. And for the D orbitals, you can see right here, since you have 5 different numbers, you're going to have 5 different types of D orbitals. And then for the F orbitals, you have 7 numbers. You have 7 different types of F orbitals. Okay. Now remember, we're assuming that the orbital is full. So from here to here, that connects to this right here. Oh, yeah. The first one here, when it has electrons and it's full, you have the first electron because you have just one orbital, the second electron, right? Since it fills up by having 2 electrons, you put 2 here. This one here, you have 3 orbitals that fill up by having 6 total electrons, you put 6 here. Okay, and so on and so forth. So I'll let you guys finish this table up. I'm moving on. Next one is asking about the outline of the periodic table and outline as well. So wait, draw an outline, an outline. Okay, but anyway, label the different areas corresponding to the filling of SPDF. Okay, SPDF. I don't know if that is in your. Oh, it is over here. Right. So not the tiny little blocks, just the big ones. So you just want to draw this right here. Just the outline ones, not the tiny blocks, right? I've had people draw the little blocks. I mean, if you can if you want to, but I'm going to use the red right here. You know, you want to draw this part here, red. Remember, this blue is really part of that, right? You want to use the blue for this one here. I mean, you don't have, sorry. Pick your own colors if you want, but what they're asking for here is shown here, right? This is number 4. So you draw that outline. And this here shows you the filling of the different electrons. The S block shows you how the S electrons are filled in the S orbital. The P block shows you how the P electrons are placed in the P orbital. And the D block shows you how the D electrons are placed in the D orbitals. Are these all still electrons? Yes. All we're trying to figure out is what type of house they live in while they're in the atom. Okay, if you think of the atom as a weird universe where there are all these electrons living in there in different houses, right? Depending on what block they're in. The ones in the S block are living in spherically shaped houses. The one in the P block are living in figure 8 shaped houses. The one in the D block, D block, they're living in a clover leaf house. And then the one in the F block are living in something that looks like a flower. It's complicated, right? And the neighborhood or the block of the electron influences the shape and the energy level and how close that orbital is to the nucleus. Remember, the S block tends to be the closest to the nucleus, and then the F block will be the furthest away. Okay, anyways, yeah. So you have the F block right here. Okay, moving on. So for this one here, it says sketch or draw the shapes of all the various. Okay, hold on just a second. Okay, so when it says here, sketch or draw the shapes of all the various orbitals corresponding to L is 0, L is 1, and L is 2. I didn't ask you guys for L is 3. So we want the shape that goes with L is 0. That's that one. The one that goes with L is 1. That will be this one here. Okay, remember, this is, let me write this in red. This block here corresponds with L equals 0. This is L equal 1. And then this is L equal 2. They didn't ask you for the shape here, but this would be L equal 3, right? Okay, so I skipped L equals 0 and went straight for L equal 1. So what you guys want to do then is, well, scoot this down and then work on L equals 0 here. So L equals 0 will be, of course, the spherical shape. And when you go in your PowerPoints, that will be, where is the shape? It's somewhere down here. Oh, so you're going to be sketching this one here. There's only one L equals 0. So you'll be drawing that one right there. Okay. Remember the axes, left and right is X, in and out is Y, up and down is Z. Then you draw your sphere right there. There's only one type of S orbital, and this is it. When it comes to the P orbitals, there are 3 types, 1, 2, 3. So I instead found this picture. You can use the one in the textbook, copy and paste. As long as you recognize it, right? You can use these ones here. Can you copy and paste this? I think so. Okay, for d orbital, you're drawing all of these for the d orbitals, right? Once again, if you don't want to just copy and put them there, you can draw it by hand. Now, it's a little tough to draw it by hand because it's hard to illustrate 3D on a 2D surface, right? On campus, my students look at me like, how? I say, just draw something that looks like this and you get credit for it. Because one class I had an artist, oh my goodness, his pictures were awesome. He got the same credit everybody else got. Okay, so that's number 5. Okay, moving on to number 6. Number 6 here, this is saying write the 4 quantum numbers in the order N, L, N sub L, M sub S for the following elements, right? And the example I gave you guys here was carbon. So you want to go, of course, start with hydrogen, helium. Okay, where do I work on this? I'll work on it right here. So let's say I have energy level, angular momentum, magnetic quantum number, and then magnetic spin or spin quantum number. Okay, I'm going to start with the element hydrogen, and then I'm going to do helium. And you guys already have carbon here, right? Okay, so for this one here, let's go to the, let's see. Oh, we have the periodic table in pieces. Okay, I just realized that we have the periodic table here, but it's in pieces. It's fine, I'll just start from the beginning. I'm gonna work on hydrogen and helium, right? So we know hydrogen and helium are roommates. So hydrogen is electron. The hydrogen corresponds with where the first electron is. And I usually write this disclaimer in class for us to work on this, okay? That the atoms in the periodic table are positioned where their last electron is in the atom, okay? Let me see. So the quantum number that we are writing here corresponds with the last electron, not all the electrons. If an element is a multi-electron element, aka it has a lot of electrons, we tend to assign it the quantum number of its last electron. Okay? So I know I said a lot of stuff, but what I'm trying to say here is the elements position in the periodic table. So I'll say here elements position in the periodic table. I'm not going to write all that because it's hard to write all that. I'll say here NPT is equal to position of last electron. So I don't mean valence electron because valence electrons can be many. I mean the last electron. Last electron. Okay. Okay. How does this play out? Hydrogen only has one electron. So hydrogen is in the position of the first electron. So once I write the quantum number here, that quantum number is not only assigned to hydrogen, other elements will have that quantum number assigned to all their first electrons. But yeah, I'm trying to confuse you guys, but Once again, the element's position is equal to the position of the last electron. So let me just go with this. This is where hydrogen is, right? So let's write the 4 quantum numbers for that. The energy level is already here because energy level is already written right here. So we'll read it across as energy level 1, right? So N for hydrogen is 1. Now, helium is right next to hydrogen, right? We're working on the roommates. When it comes to quantum number, helium and hydrogen are rooming together. So helium is also on energy level 1 or row number 1 or period 1, right? So this is also 1. Okay. Now, let's find the value of L. I'm going to scroll over here and once again put where hydrogen is and then where helium is. So helium is right here. Once again, so for this part here, remember the value of L is equal to 0. So since hydrogen and helium are in the same block, the L value will be 0 here, 0, right? Because they're in the blue block where that's 0, and this will be 0, okay? Moving on, let's find the N sub L for the periodic table. There. Once again, I'm working on hydrogen and helium. They have the same N sub L values because they're roommates, okay? So what I tell my students in class is this. Imagine you and your brother lived in, or maybe you and your sister, you and your sibling, how about that? You and the sibling who live in the same house. I just thought about it. You and your sibling are sharing your room, are sharing the same room, right? And you live in the same house. But mail comes to both of you. Now, because you're in the same house, the mail will have the same address. So then if that's the case, how do we know the mail is assigned to you? It will have a different name on the address. So the first 3 quantum numbers code to the address of the orbital. And the last quantum number is kind of like the name, not really, but it specifies which electron we're talking about, right? Okay, so they're in the same orbital. The first 3 quantum numbers have to be the same. The N sub L value here goes with 0, and that's 0. So 1, 0, 0, 1, 0, 0, that goes with the first and the second electron. Now, M sub S, that will go with the last quantum number, which I gave you this table for, right? This one here. Yeah, so this is going to be hydrogen, and this is going to be helium, and that's how we tell them apart. Hydrogen representing the first electron and all first electron, helium representing the second electron because it has 2. So the last electron is what tells us, is what is assigned to helium, okay? So hydrogen has a positive spin. So this positive spin here will be written as positive 1/2. Helium is assigned a negative spin, negative 1/2. And this is used as an identifier. Okay, so this is how we can tell the 4 quantum numbers for hydrogen and helium, and we can tell their roommates or orbital mates because the first 3 quantum numbers are alike. Okay, let me go ahead and finish this because I'm beginning to power down. Okay, technically this is in chapter 3 where it says use the periodic table to write the electronic configuration. So what I'm going to do right here is go to chapter 3. Hold on a second. Okay, we're back. When I say we, I just mean me. It's just me here. Okay, so I found the chapter 3 slides, and I just wanted to show you guys here. Okay, remember the first part I mentioned that was in chapter 3? The one about Mendeleev. Let's see, it should be somewhere here. Yeah, it mentions him. So you can go ahead and summarize that part, and then summarize this part here. And that answers this part, right? That answers number 1. Okay, so moving on to the part that's relevant to where I was. We're now looking at this part here, electronic configuration. So my assumption here is you've done all this work here. And I'm going to jump straight. I'm trying not to make this too long, right? So I'm going to jump straight to the electronic configuration. For the configuration, remember, the configuration is unlike the quantum numbers. Quantum numbers code to 1 electron at a time. You're looking at every electron individually at a time in the element, okay? For the most part, when you write a quantum number for the 4 quantum numbers for the element, you're writing it for the last electron. Electronic configuration is more like an electronic distribution where you're distributing the electrons in different sublevels. So you have to know what the sublevel is to know how to place the electrons in the sublevel. Now, we kind of covered this before where we said back here that these sublevels, when they have, we didn't call them sublevels, we just call them, we just call them SPDF, right? So when S has electrons, it can house a maximum of 2 electrons, right? We didn't use the term sublevel here. When P has electrons, it can have 6 electrons. When D has electrons and it's all when all the D orbitals are maxed out with electrons, it can have up to 10 electrons. When all the F orbitals are maxed out with electrons, it can have up to 14, right? Because you have 7 orbitals. Okay, now this picture here takes this concept and builds up on it right here. So now we're seeing the idea of sublevels. So what exactly is a sublevel and how is it written out? So here we're seeing that the sublevel, remember the orbitals are like rooms. The sublevel are like, I can't really say that they're complete floors. It's not really a floor. It's more like a wing, okay? Because the energy level will be like a floor. And so in the floor, on the same floor, there's the different spaces, kind of marked out spaces. So those spaces that are marked out are sublevels, okay? So in the sublevel, you have, let me try to give you, I'm trying to explain this well, but I feel like I'm kind of getting lost. So let me give you an example of energy level 3 sublevel. Okay, that's a good one. Energy level 3 sublevel, there are 3 sublevels, okay? So for energy level 3, we have 3s, because we said it's energy level 3. That means N. N is a symbol that indicates the energy level. It tells you about, it just tells you this is the energy level. That's what the designation is here. So for energy level 3, we have 3 sublevels. 3s is the first sublevel. 3p is the second sublevel. 3d is the third sublevel. Okay, so over here, all we were doing was just talking about the sublevels in general. We were not tying them back. While it says orbitals here, the orbitals are on sublevels. I'm really trying to make sure this is not confusing. Okay, so imagine that in this atom, you have the energy level, and the energy level is N equals 3. Okay, so I'm going to be drawing this for the hydrogen atom only, because in the hydrogen atom, this concept, this idea is very simple. In the hydrogen atom, where you have only 1 electron, the energy level, which is like the floor, tends to house all the sublevels. So you have 3s on the same level, so that will be here, right here, 3s, 3p on the same level. Remember, 3p has got 3 orbitals, right? P tends to have 3 orbitals. That's what we said here. So that's what I'm drawing 3 boxes. The 3 boxes here match the number of orbitals. And then 3D, which down here will have 5 boxes because it has 5 orbitals. I'm going to draw that right here. 1, 2, 3, 4, 5. Does that make sense? And remember, in each of these boxes, orbitals, that's where you have your electrons staying. And if the orbital is full, you have 2 electrons. Okay. Whew, I'm trying to get to something here. Okay, so that being the case, how does this translate into this? We have 3s, 3p, 3D. Somewhere here in the lecture, it does mention, so remember what I was telling you earlier, this is it for hydrogen atom, those sublevels are in the same level when they're in the same energy level. Now in this picture here, instead of using the term energy level, which chemists do, and it gets on my nerves when you're still learning it, the shell here is the same thing as the energy level. Energy. Okay, so when it's saying shell 1, it's the same thing as saying N equal 1. So at energy level 1, we only have 1 sublevel, that's 1s. At energy level 2, N equal 2, we have 2 sublevels, 2s, 2p. Energy level 3, when N is 3, we have 3 sublevels. This is what I try to draw over here. Please don't judge my drawing. I really try. Okay. Energy level 4, we have 4 sublevels for S, for P, for D, for F. Okay. This is energy level 4. Okay. The energy level is written in this convention. So the format of writing sublevels is you write the energy level first, and this has to be a number. And then you write the angular momentum or the azimuthal quantum number next. And that's going to be the L. This has to be a letter. So it's going to be one of the S, P, D, or Fs like that. And the energy level. So it has to have those two quantum numbers together communicate to us. This is the sub level. Does that make sense? If it doesn't, go back and review the lecture. Okay. Anyway, so we are placing the electrons in these sub levels. I just show you. Now remember, each orbital can max out at 2 electrons. So I'm going to write the max here. When you have s orbitals, which is shown here as boxes instead of the actual shape. Remember, in the actual shape of the orbital is round, right? Here they show it you as a box to make it simple. If each of these orbitals have electrons and is maxed out, that means it has 2 electrons, right? Up, down, 2 electrons, up, down. So the max you're going to have here for the s orbital is 2, for the p is 6 because each box holds 2. For the D is 10. For the F is 14. I feel like I'm teaching this instead of going over the lab. It's just because I'm going to let you guys finish the rest of these. So remember, this represents the s orbital. So you can have 2 electrons here, up, down. These represent the p orbital. So this would be 1 orbital, 2nd orbital. I'm drawing like this so you can see the marks. Then 3rd orbital, px, py, pz. Then these represent the d orbital. 1st, 2nd, this is -2, -1, 0 for the m sub l, right? 3rd, 4th, 5th, okay? Okay, having done all that, now we're trying to do what? Where was I? I know, I went off tangent. I'm trying to write the electronic configuration for... Let me do carbon this time. Did we do carbon before? Yeah, let me do carbon. Okay, so the periodic table, hello, Helena, a little bit, Bora, Chinjana. Okay, carbon is right here. I know. We had to memorize the first 20, so I was just trying to do that. Bora, Chinja. Okay, so carbon is right here. Okay, so the carbon being right there, the configuration, we're going to write the configuration talking about where the electrons are placed until we get to carbon. So carbon has 6 electrons, right? So the first electron is going to be here, 2nd electron will be here, 3rd here, 4th here, 5th here, 6th here. Okay? So for the configuration, you will write in the first sublevel, that's labeled 1s, right? This is called 1s sublevel. We're going to place 2 electrons. The next 2 electrons, electron 3 and 4, are placed in the 2s sublevel, and that's going to be replacing 2 there. Then in the 3rd sublevel, and when you're filling, you go from left to right, okay? So fill the 2s here, then the 2p. In the 2p, while 2p can hold up to 6 electrons, we are only placing 2 for now, okay? So 2p2. Now, I haven't applied a Hund's rule. No, because Hund's rule has not been stated here yet. That will be shown later on. That will be discovered later on, okay, where it kind of complicates things. So right now, I'm not applying Hund's rule, the degenerate orbital. So 1s2, 2s2, 2p2, and that's it. And you guys can figure out the rest of these, right? For this last one here, okay, let's see. Oh, I need to mention this. For platinum, this is actually stated down here somewhere that platinum tends to be the exception to the rule where you cannot really use this periodic table process to figure out the configuration. There are some exceptions there. So for platinum, you actually kind of want to just go online and find it, okay? Because it says so somewhere here in the lecture, and I don't know where that is. Oh, it mentions it somewhere here. Transition metals with irregular configurations. So platinum will be one of those where the configuration is irregular. And so you can't really use the periodic table to figure it out. So you have to do it experimentally, which you can't do it experimentally. So that means you have to find it online. And you see what the irregularity is, okay? So platinum is like palladium, where scientists expected to have this based on following the rules of the periodic table. But what they found experimentally was this. So this is what we have here on the right is the true configuration of palladium, right? Versus expected. This is what they were expecting. This is what they got. Right. It reminded me of something I want to share. But yeah, anyway, yeah, expectation, right? And then this is what you got. And so the assumption here is since fully filled sublevels tend to make the molecule more stable or the element more stable, the element will sacrifice the 2 electrons here by moving them over here because it wants to appear more stable. Okay. Yeah. So once again, platinum really falls under here where the true configuration cannot be determined by using that chart I showed you earlier, right? So you want to just go ahead and Google and write that down. I've been asked before, shorthand or longhand? Write the longhand configuration. Actually, it will help for you to write both, but the requirement here is longhand configuration. Okay? Even though I happen to show the shorthand here. Okay, this last one here is asking you complete the following table of first ionization energies for the elements from group 1A and group 2A. So these are 1A and this is kind of 2A right here. So I think there is a chart somewhere here in your book. I think. Hold on. I know this is just a graph. That graph is similar to your lab, right? So that it should hit different. Anyway, yeah, you have these numbers right here. So you have group 1 numbers, right? The elements here, of course, you copy from here: hydrogen, lithium. Oh, I've also been asked this in lecture before. I mean, when I say lecture, I mean on campus. Should we include helium here in group 2? No. Helium only fits here in quantum numbers, not in periodic properties. So K, RB, and then CS, right? And then we're going to write, because this one goes with first ionization energies, you have your units right here. So that will be 1312. This is, of course, kilojoules per mole. Right? So you write the number here, 520. So you're just copying these numbers here. For this one here, of course, you're going to start with beryllium, magnesium, calcium, strontium, barium. Okay? I'm struggling to write. Atomic number for these ones here, atomic numbers. Find the periodic table and put the atomic numbers in there. I know it's 1, 3. I think this is 11. Something, but anyway, yeah, find the atomic numbers and then put them in here. I mean, atomic number goes here. You're gonna then prepare a graph of ionization energy being the y-axis. So you have a y-axis, which should be ionization energy, and then the x-axis will be atomic number. Now you can combine the two of them on one graph if you want, or you can draw them in separate graphs. Okay. And then you want to talk about how the ionization energy relates to atomic number. You see the trend. I want to tell you what the trend is. Which group is more reactive? We saw this in an experiment earlier, right? That is group 1 because their ionization energy is a lot lower. So it's easier to remove the electron from group 1 versus group 2. And we saw in the experiment reactivity increased to the left. Oh, you see how these things is tied together, right? And then, yeah, which group is more reactive? It would be group 1. Why? Because it has a lower ionization energy. So the higher the reactivity, the lower the ionization energy. Okay. And then that wraps up. So you want to include your graph here. You can take a picture of it and post it here. Or if you do it in Excel, just add it here. It will not be a straight line graph. Okay, but you can add it here, and then that wraps up this lab. So hopefully this has been meaningful. Okay.